All right, now that we've talked about how to search for locations using a 2D index, I want to go over a more sophisticated type of geospatial indexing, a spherical geospatial indexing that is also supported in MongoDB. Now, to start out, before you can talk about finding things in a 3D world, you have to talk about how you describe the location of something in a 3D world. So the world is actually a globe, and this is my poor representation of the globe. And locations on the globe are represented by longitude and latitude. So if you recall, latitude is how far off the equator is the object. So for instance, the equator is at 0 degrees latitude, and you can go all the way from minus 90 degrees to 90 degrees. And that's your lines of latitude. And then we have the longitude. And the longitude, this is a line of longitude right here, it describes a line that goes from the North to the South Pole. So in order to describe the location of any particular object on Earth, you need its latitude and its longitude. Now, in addition, we're going to need a way of indexing these documents that have latitudes and longitudes in them. And the way we're going to do that is a new special type of index called 2D sphere. So let's talk about how we're going to do this. And I think the easiest way to get into this is by example. So I'm going to go through an example of a few locations that have been put into MongoDB documents. We're going to search near a location to find the closest locations. And we're going to use a 2D sphere index to do it. So let's start with the locations. So here's Palo Alto. And in Palo Alto, we've got 4 locations that are near and dear to my heart. We've got Fry's Electronics, where I used to get small electronics components before people stopped building anything in the late 90s. And the Peninsula Creamery, where you can get a great milkshake and a burger. The Apple Store, where you can spend a lot of money. And Hoover Tower, which is a monument right in the center of Stanford's campus. And then there's one more location that I put on my little map, and that is Mount Tamalpais State Park. At the top of Mount Tam is where I got engaged, so also a place near and dear to my heart, a little bit further from Stanford. And we're going to put documents into MongoDB that represent these locations. All right, the first thing I want to show you is that Google Maps is very convenient for finding the latitude and longitude for locations. So let's look up Times Square, which is where we are right now. You'll see that what Google Maps will do is in the browser URL, it'll actually show you, and we're right over here somewhere. It'll show you the latitude and the longitude. Now, it shows it to you in latitude, comma, longitude order. So latitude is 40.75 here, and the longitude is minus 73.98. This is in the opposite order you're going to need it when you specify them in MongoDB. MongoDB takes a longitude, comma, latitude. All right, so how are we going to specify the locations of things? Well, we use a location specification called GeoJSON, and I'm going to show you that right now. This is a web page on GeoJSON at geojson.org. We implement only a small part of the specification on GeoJSON, but if you want, you can look at it and see the full specification. And in particular, the parts that we're going to be most interested in are the parts that specify points and geometries, and you can see there's coordinates and lists of coordinates. It's kind of a complicated thing when you've got, especially if you want to describe a polygon. We're only going to do the most introductory lesson here right now, and then you can go look further if you want to see what all the different possibilities are. And MongoDB only supports a subset of these, like points and polygons. We don't support some of the more complicated structures. All right, so let's go into MongoDB now and see our documents. So I put them in a collection called Places. So here we are. I'm going to pretty print them, and we're going to see the GeoJSON format at work. So here we have the Apple Store. I decided to specify the city of Palo Alto. I decided to put my GeoJSON location information into a key called location. This was my own decision. It's arbitrary. But you can call it anything you want, but I called it location. And then everything after this paren and to this closing paren, that's a GeoJSON document. In this case, I've decided to describe it using a point. You could also describe it using a polygon if you wanted to give it some area, but we described it using a point. And the type is a reserved word, and coordinates is a reserved word, point is a reserved word. And here are the coordinates in longitude, comma, latitude order, which I got from Google Maps. I decided to put that it was a retail store into the collection. Again, we've got 4 objects in the collection. We've got this Apple Store, this Peninsula Creamery, and Fry's Electronics, and then finally Mount Tamalpais State Park. Okay, so in order to query this, we're going to need an index on the GeoJSON documents. So let's do that. db.places.ensureIndex, and it's going to be on location, and it's going to be of type 2D sphere. Never understood why this is called 2D sphere. It seems to me that if you have a two-dimensional sphere, that would be a circle. But what I think is trying to be expressed here is that although it's a 3D model, it's a spherical model, that it's only looking at points on the surface of the sphere versus up in the air. So that's why it's called 2D sphere. So we're going to add that. And now there are two indexes on the collection, which is all good. Previously there was one. I can show you the indexes. Hold on. Get indexes. The indexes are this underscore ID index, which always comes with every collection, and then this index on location. So what query might we want to run? Well, I want to know the closest things to me, and I'm standing at Hoover Tower in my imagination. So let's go through that. I'm going to quit from the shell here, and I've got a query that's been written out already to make it a little bit easier to follow. So this query is going to search the places collection right here and do a find. And it's going to find documents by location, which is the field that we created to hold the locations of the various stores. And it's going to use the $near operator. Now, the $near operator is going to search for everything near a point, in this case. Now, this $geometry is a required operator, and you can also give $max distance, which is the max distance in meters. I said 2,000 meters. Find me everything that is closest to these coordinates, minus 122, 166, 641 degrees, longitude, and 37 degrees, 0.427, blah, 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 latitude. And these are the coordinates of Hoover Tower that I got from Google Maps. So again, if you just to look at the format of this, we had a find. We specified that we're looking at the location field. We're applying the $near operator. And then we have a GeoJSON document that has specified the geometry of type point with these coordinates. And that's it. So let's see what we get when we do that. So Mongo, I'm going to just redirect from this file to run this query. And it looks like we got back two documents. And these are going to be sorted in order of closest to furthest, which is a feature of the $near operator. The first one is the Peninsula Creamery, and it is in fact closest to Hoover Tower. And then the Apple Store, which is also within 2,000 meters of Hoover Tower. Notice that it eliminated Fry's and it eliminated Mount Tamalpais as being outside 2,000 meters. All right, and just to review that with you, to show you the map again so you see that this is the right answer. Remember, we were looking at things closest to Hoover Tower, and it said that within 2,000 meters, you've got the Peninsula Creamery at closest location and Apple Store next closest. Fry's and Mount Tamalpais are off the screen. Fry's is on the screen, but out of the search radius, and Mount Tam is completely off the screen. And that's how you would actually search for something using the near operator. So again, the secrets are that you need to know the latitude and longitude of your documents. You also need to create a 2D sphere index if you want to use the $near operator. Some of the operators don't require having an index, like for instance finding something that's within a shape, but they all perform better if there is an index on the location. And then you need to, of course, insert the locations and perform the query. Okay, let's now do a quiz. What is the query that will query a collection named stores to return the stores that are within 1 million meters of a location at this latitude and this longitude, latitude 39, longitude minus 130? Type the query in the box below and assume that the stores collection has a 2D sphere index already on it, on the key location, and use the $near operator as we did in this lesson. And if you're looking for what the documents look like, this is an example document. Might have an underscore ID that looks like this, with a store ID of 8 and a location of type point, and these are the coordinates. So you have to write that query right here and then hit return and see if it's correct. You have to be pretty careful to make sure it's exactly the same because we're going to pattern match against that.